at the problems in the midterm. Okay, I think the first problem. So I'm doing it by memory. So if that is a little bit off, just correct me. Okay. So I think the problem, one of the problems was there were two students who write an exam, and there's one question. Um, the probability. So it's something like A and B write. A and B answer one question. So probability they both probably I think it was the probability each one gets the answer is P, and probability exactly one. P over 3. Oh, what happened?
Yeah, the video too.
Oh, sorry. No. Let me just restart. Just 1 second. Let me also. Okay. Just give me a second. Let me make this a little more. Okay, so the midterm question was that A and B answer one question. Okay, the probability that either one of them, probability each one of them gets it right, is P. Okay, and the probability that exactly one of them gets it right is P over 3. Okay, it's something like this. So why don't one of you help me do this problem? So how would you write the universe?
I said that so I said a 0 is they get it wrong, and a 1 is that they get it right.
Okay.
So then I have P1, huh?
Right, so maybe we have two Bernoulli random variables, xa and xb. Xa is 0 if A gets wrong, then 1 if A gets right. And similarly for xb. Okay, now what will be the universe? Can you continue, Axel?
0, 0, 0, 1, 1, 0, and 1, 1.
Okay, so these are all the possible combinations. So how do we write this event? Probability A gets it right. Right, so this is the probability xa equals 1, and this is P. Okay, and this is the event 1, 0, 1, 1. Okay, and probability B gets it right, it's the same. This is the probability xp equals 1, and this is also P, and this is the probability 0, 1, and 1, 1. Okay, what's the probability exactly one gets it right? What's the event that exactly one gets the answer right?
0, 1, and 1, 0.
So this is the probability of 0, 1 and 1, 0. This is P over 3. Okay, so now, right, so now we need to write a probability distribution that is consistent with all these statements. Okay, so can anyone help me continue? You did this, all of you did this problem, right? So can you, so it doesn't matter if it is right or wrong. In fact, it would be even better if it is wrong. Okay, so, but can you help me continue? Like one other thing, like if you, also if you get your answer wrong, don't worry, like I don't grade in a binary fashion. So anything that you have done, like you're going to get credit. So you'll probably get way more, even if you have got things wrong, your score will probably be much higher than you think. Okay. So, okay, but can anyone help me continue? That's it. Yeah. Okay, so what Brandon is saying is like, okay, so I'll just write it in a slightly different way. So Brandon, that's very good. So that will get you the answer. So let's call these probabilities like W, X, and Y. Okay, the probability of 0, 1 as W, probability of 1, 0 as X, and probability of 1, 1 as Y. Okay, now this means that, so what's the probability A gets the answer right in terms of W, X, and Y? X plus Y, right? And what's the probability B gets the answer right in terms of these? W plus Y. Okay, is everyone okay with this? Okay, so and the probability exactly one gets it right is W plus X. Okay, so we have X plus Y is P. W plus Y is also P, and W plus X is P over 3. Okay, from these three equations, you need to solve for W, X, and Y. Okay, and how do you do that? Like Brandon was saying, just add up these two equations. So you get W plus X plus 2Y is 2P. Okay, but you already know X plus W is P over 3. Right, so this means that 2y is 2p minus p over 3, and y is 6p over 7. 7. How much is y? So 2y is uh, what will be 2y? 5p over 6. Yes. Yeah. Yeah. Okay. 5p over 3, and y is 5p 6. Okay. So y is 5p over 6, which means that using this, w is p minus y, which is p minus 5p over 6, which is p over 6, and x is p minus y, also p over 6. Okay, and this means that w plus x plus y is 7p over 6. Okay, if it is 7p over 6, like that's why I told you that p is less than 6 over 7. Okay, so there's no contradiction, right? And so this is 1 minus w minus x minus y. Okay, so is everyone okay with this? right? So this universe, the probabilities are 0, 0, 0. I mean, the probabilities of all of these. This is 1 minus 7 p over 6. This is p over 6, p over 6, and 5 p over 6. Okay, and ask you something like ask you what's the probability A gets it right, A is right, given that at least one is right. Right. So what is this conditional probability? Right. So this is the probability A is right and at least one of them is right. No. Let's be a little careful. Probability at least one is right. Okay. So what is the probability at least one is right? What's the event that at least one is right? No. What's the event that at least one is right? Justine, like, no, at least one should be right. So is at least one right in this? Yeah, right. So here B is right. So at least one of the students is right. Here A is right. So at least one of the students is right. Here both are right. So again, at least one of them is right. Okay. So this event is 0, 1, 1, 0, 1, 1. Okay. The A is right and at least one of them is right. Right, so this is the intersection of 1011 with this set, and this just happens to be the probability. And this is the event that A is right, and intersection with at least one is right. Okay, and this is just uh, the same event. Okay, it's just the event A is right. Okay, because if A is right, at least one of them is automatically right. Okay, so the conditional probability. Okay, this is the probability of 1011 divided by the probability of 011011, right? And so this is p divided by 011011 is 7 p over 6. So this is 6 over 7. Okay, does that make sense? Right, so is everyone okay with this? Right, so particularly like so Keith, Samuel, Justine, right? So don't worry. I mean, don't worry if you're like I said, like when I do all of this, like don't stress out if your answers in the quiz is in the midterm is wrong. Okay, that doesn't matter. Like if you're on the right track, you'll probably get way more credit than you expect. Okay, but is everyone okay with this? Okay, um, right. So the next problem was about independence and so on. It also lets us segue into the uh, next topic. Right? So it was something like this: like we are going to use a binary erasure channel 3 times, okay, and we are going to transmit a bit. Okay, the reason is that when you have a not erasure, I think we did symmetric, right? Uh, right? So this is the input to the channel and this is the output, okay? And right, so the probability, we'll call this X and we'll call this Y, as per the problem. So the probability y equals 0 given x equals 0 is, I think I wrote it as probability y is not equal to x given x 0 is epsilon. Right, so this is how I specified the probabilities. But here, like this is exactly equal to probability y equals 1 given x equals 0. This is also probability y equals 0 given x equals 1. Okay, y is not equal, y can only take two values, 0 and 1. Okay, so if y is not equal to x, you know what y is. Okay, so this is epsilon, this is epsilon. So what is the probability y equals 0 given x equals 0? Very good, 1 minus epsilon, and probability y equals 1 given x equals 1, also 1 minus epsilon. Right? And we know this because these two probabilities have to add up to 1. Okay, they're both conditioned on x equals 0, and y equals 0 and y equals 1 partitions the universe, so they should add up to 1. And these two conditional probabilities should add up to 1. Okay, good. So the other thing I told you was like we are going to use the channel 3 times. Okay, but conditioned on an input. So we are going to send the same input 3 times. Okay, so we are going to use at time equals 1, time equals 2, time equals 3, we are going to use the channel. Each time we send the same bit. Okay, and the first time we use the channel, we maybe get x by 1. Second time we use the channel, we maybe get y2. Okay, the third time we use the channel, maybe we get y3. Okay, now even though we send the same input all 3 times, okay, your outputs may be different. Okay, because the channel introduces an error at random with probability epsilon. Okay, so sometimes it may introduce an error, sometimes it may not. Okay, so for example, so here I also told you that the joint probability of y1, y2, y3 given any of these inputs is y1 given x times probability y2 given x times probability y3 given x. Okay, so each conditioned on an input, conditioned on the inputs of the channel users are independent. Okay, and then I asked you, okay, given x equals 0, if your bit is 0, write the probability distribution for y. Okay, so what is the probability distribution for y? If x equals 0, what are the values y1, y2, y3 can take? Right. So,
Yeah.
right, so it's like all combinations. Right, so the bits y is either 0 or 1. Okay, now regardless of whether x equals 0 or x equals 1, y1, y2, y3 can be all 8 sequences. All 8 sequences are possible. Okay, now we don't know what the probabilities are, but our universe contains all these 8 sequences. Okay, now what is the probability of y1, y2, y3 being all 0? Okay, so this is the probability y1 equals 0, y2 equals 0, y3 equals 0 given x equals 0. But very good. So I told you that this is the product of the right. So this has been given, right? So and this would be right? So this would be 1 minus epsilon cube. Okay, so what's the probability of 0, 0, 1 given? So this is the conditional probability of y1, y2, y3 given x equals 0. Okay, what's the condition? What's the probability of 0, 0, 1 condition on x equals 0? Very good. Epsilon times 1 minus epsilon squared. Epsilon times 1 minus epsilon squared. What is the probability here? 0, 1, 1. Very good. Epsilon squared times 1 minus epsilon, epsilon times 1. And this is epsilon cube, right? So this is the probability distribution of y1, y2, y3 given x equals 0. Okay, and similarly, you could write the probability of distribution of y1, y2, y3 given x equals 1. Okay, but in the first one, right? So what is the probability we make an error? Okay, now what do we do? Our estimate of what the input is, okay, it's the majority among the bits of y1, y2, and y3. Okay, so, okay, so let's write our estimate of what the input bit was. Okay, if y1, y2, y3 are all 0, what is our estimate of the input? 0. What is my estimate here? Again 0. What is my, so here also again 0. What's my estimate if the input, if the bits are 0, 1 and 1? It is 1. Okay. Here again it is 0, here it is 1, 1, and here it is 1. Okay. Everyone okay with this? Okay. So then I asked you, what is the probability that x hat is not equal to x given x equals 0? Okay, what is the event? So if condition on x equals 0, what is the event x hat is not equal to x? Right, so here x is equal to 0, right? So is x hat equal to, is x hat not equal to x? So here, these are the bad events, these are the bad situations. These 4 rows, our estimate is not what was transmitted. Okay, so this one will be the probability of 0, 1, 1, 1, 0, 1, 1, 1, 0, and 1, 1, 1 given x equals 0. And this probability is 3 times epsilon squared times 1 minus epsilon plus epsilon cubed. Okay, this is the probability you make an error. Okay, and you could simplify it. So this is epsilon squared times 3 minus 3 epsilon plus epsilon. Right, so this is basically the probability we make an error. Okay, so imagine epsilon is very small. Okay, when epsilon, so in general, the probability that you make an error in any single channel use is epsilon. Okay, but when you take the majority among 3 channel users, your probability of error is roughly epsilon squared. Okay, so that means that, like, if your epsilon was something like 10 to the minus 3, okay, if you do one channel use, you have a 10 to the minus 3 chance of making an error. Okay, but if you take the majority decision, you have you have taken it down to the order of 10 to the minus 6. Okay, so that's why like using this majority right, so using this majority this one, it reduces I mean it's like 3 times 10 to the minus 6, but it's still okay. Okay, so which is why like these majority decisions, like they drive down the probability of error. Okay, but it's something you should keep in mind because when you download like a file from the internet, okay, you download files that are like several gigabytes or something like that, so that is completely normal. Okay, gigabyte is something like 10 to the minus 9 times 8 bits. Okay, now in all of these even though you download such a large file and you have done it for so many years, okay, you never get a file that is different from what was transmitted. Okay, and the channels we use on the internet, they are very imperfect. Okay, so every link, there's a probability that something can go wrong. Okay, and every link is very unreliable. So even though every link of your communication setup is unreliable, you manage to get like an overall transmission that is extremely reliable. Okay, and this is one of the this is like a major engineering breakthrough. Like it's like so you do use something like this. You don't use exactly this majority decision. It's kind of wasteful because in order to send one bit, you have to use the channel 3 times. Okay, we could do far better and we could improve this. We could drive down this error probability even more. Okay, if we use more sophisticated schemes. Okay, but it's a useful principle to remember, right? So does this make sense? Okay, so the last part of this problem was what's the probability that x hat is not equal to x? Okay, how do we do this? Right, so I haven't told you what is the probability x is 0 and what's the probability x equals 1. Okay, but how can we do this? What's the probability x hat is not equal to x? Right, so also like you will also have I mean the whole thing is symmetrical, so you'll have this exact same story. Given x equals 1 is also the same thing. Right, so how do we compute what's the probability that x hat is not equal to x? Okay, what we know are these two. Right, there. Okay, so
Would it be the same? Like if x is equal to 0 and then
right, but how do we do it formally? So there are two answers here, right? So one is, so we want to use, so clearly this is the only thing we have computed. So we want to use this to compute, right? So to come to, so, right? So formally, how do we relate? How do we relate? Right. So this is not true, right? So very good. So this plus this equal, right? So this plus this is not equal to 1 necessarily. Okay, in fact, like when epsilon is small, these two are the same value, and their sum is something like 2 epsilon squared. 2 epsilon squared times 3. Okay, so clearly not equal to 1, right? So because you cannot so when you condition on different events, that is x is 0 and x equals 1, okay, their conditional probabilities may not be directly related at all. Okay, so this is generally not true, so this is like a dead end. Okay, so how else can we use these to, how else can we relate these conditional probabilities to this probability x naught is not equal to 2x? Right, so Brandon, you're right, but can you tell me how to relate it in general? Okay, so here like we have conditional probabilities. Okay, so let's write it in terms of joint probabilities. So what is the joint so how do I relate it to this joint probability? Right, so can you tell me how to relate this conditional probability to the, I mean, we have, there are only very few things in our toolkit. Okay, so how do you relate this to this joint probability? Okay, I divide by probability x equals 0, right? So let me write it this way. Okay, or let me write it like this. We do not know probability x equals 0, but that's okay, like we'll wait. Okay, so same way, what is this? Okay, now can you relate these two to the probability x naught is not equal to x? Right. So the events x equals 0 and x equals 1 partitions the universe. Okay. And I'm taking the intersection of these with, right. So here I'm looking at x equals 0 and x equals 1. It's a partition of the universe. Right. And I'm taking the intersection with okay. So this term, this red term, okay, is exactly here, and this green term is exactly this. Okay, now if I add the red and green parts, like I should get the probability that x hat is not equal to x. Okay, on the right side, this now becomes probability x hat is not equal to x given x equals 0 times the probability x equals 0 plus the probability x hat is not equal to x given x equals 1 times the probability x equals 1. Generally speaking, we cannot proceed further. Okay, but here lucky for us, both of these quantities are the same. Both of the same. Right? So both of these quantities, they are equal. Okay? And they're both equal to epsilon squared times 3 minus 2 epsilon. Okay? And this means that it's just epsilon squared times 3 minus 2 epsilon times probability x equals 0, probability x equals 1. We may not know the probability x equals 0 or the probability x equals 1. Okay? But we do know that they add up to 1. Right? So the probability x naught is not equal to x is actually the same number. Okay? Does that make sense? Right? So we don't need to assume anything for the probability x equals 0 or something. Okay? Here it automatically works out. Okay? Right. So, but the most crucial thing here is to recognize this part. So we have done it in class before too. Okay? But more we see it, the more we'll get familiar. Okay? If you want to move from conditional probabilities like this to this unconditional probability, okay, you're going to use some sort of variation for the law of total probabilities. Okay, now you can see the law of total probabilities in any way you want. Okay, but if you want to do it step by step, okay, what you move is like go from these conditional to joint probabilities, then recognize that the two joint probabilities will just add up to what you exactly want. Okay, so this pattern of what we did, we have done it actually a few times before. Okay, and it's actually pretty important. Okay, so are we completely okay with this?
Just to clarify, when you added the red and the green, that was you were using the law of total probability, right?
Right, so it corresponds to this Venn diagram. The red shaded area of that is the intersection between the event. So the black circle is the event x naught is x hat is not equal to x. Okay. The red shaded area is exactly the red probability. The green shaded area is this green probability. When you add them up together, you get the probability of the event x hat is not equal to x.
Mm-hmm.
Right?
Yeah, and that is the law of total probability, right?
Yeah, that's the law of total probabilities. Yeah. Yeah. So instead of just using it as a formula, we are just using it like, I mean, we are just redoing this entire thing. Okay. Uh, because at the end of the day, like there aren't too many different things. Okay. So this is a different way of stating that is some of the probabilities of a, rather the sum of probabilities of disjoint events equals the probability of their union. So it's just like a fancy way of doing that. Okay. Okay. So let's go on to one additional question. So in this I want you to think about. We won't do it right now. So I told you that y1, y2, y3 conditioned on x. So when I conditioned on x, okay, are independent. So we have probability y1, y2, y3 given x is the probability y1 given x, probability y2 given x, probability y3 given x. Right? So as long as you have this conditioning on x, okay, it behaves like independent random variables. Okay, y1, y2, y3 are independent, conditioned on x. Okay, but what I want you to ask, what I want you to think about, okay, this wasn't in the midterm, but I want you to think about this. What is the joint distribution of probability y1, y2, y3 when you do not condition on x? Okay, you can assume for this you'll need the probability x equals 0 and the probability x equals 1. You can assume that the probability x equals 0 and probability x equals 1 is 1/2. Okay, and are y1, y2, y3 independent? Okay, so here you'll find that the answer in general is no. Okay, so even though conditioned on x they are independent, okay, when you do not condition on x, okay, they actually are dependent. Okay, so but I want you to think about these questions. Okay, like, so we'll continue with where we were looking at, and we'll introduce one more discrete random variable, and it's actually the last discrete random variable we'll introduce. That again, all our discrete probability laws, they are very closely associated with Bernoulli random variables. So here x1 through xn are independent Bernoulli random variables, just like in the binomial setup. Okay, so we think of 0 as failure and 1 as success. Okay, so it's something like you're trying something. Every time the result is independent. Okay, so you're trying to roll a 6, for example. Okay, there's a 6-sided die and you're trying to roll a 6. Okay, so you keep rolling the die. Okay, your different rolls, they are independent. Okay, the first time maybe you see a 3, second time you maybe see a 1, so on. Okay, but you're going to keep rolling it till you succeed. Okay, so in general, a priori we do not know the number of random variables here. Okay, so but we are going, so you have a sequence of random variables that are independent. Okay, they're all Bernoulli P. So you're going to keep trying. Okay, you're going to keep trying till you succeed. Okay, how many trials do you need before you succeed? Okay, so here we have Bernoulli P random variables x1, x2, they're all Bernoulli P, which means that the probability of success, okay, so the probability any xi, any trial will lead to a success is P, independent of others, because we know they are independent. Okay, what's the so let's define this number t, or we'll use t. Okay, this is the random time okay, so t is a random variable. It defines the random number of trials you need before you succeed. Okay, so for example, what's the probability t is 1? What is the event t equals 1? What is the event that t equals 1? Right, so our universe here is all these x1, x2, so on. A priori we don't know the number of random variables, okay, because we don't know how many trials we'll need to succeed. Okay, right, but what is the event that t equals 1? Right, so yeah, so Brandon, that's very good. Okay, but what is the event that t equals 1? Right, so you t equals 1 means that you do only one trial before you succeed. Okay, so how can that happen? It must happen that your x1 must be 1. Okay, what is the event that t equals 2? Okay, so very good. So it's not okay. So one suggestion naturally is x2 equals 1. Okay, but is this the event t equals 2? Right? Because the event x2 equals 1, okay, corresponds to x1 equals 0, x2 equals 1, and uh, or rather the union of these two. So we don't say anything about x1. Okay, since we don't say anything about x1, it includes all possibilities for x1. Okay, if x1 equals 1 and x2 equals 1, what is this random variable t? Right, so the
Can
first,
you explain why there's a union? Like I get like the first part, like where x1 equals 0 and then x2 equals 1. But like if you had x1 equals 1, then you wouldn't perform the second trial, right?
no, yeah, I mean, like, we don't say anything about the second trial. Okay, but the second trial is irrelevant to the event t equals 1. Okay, because whatever happens in the second trial, t will, I mean, if x1 equals 1, okay, it doesn't matter what happens in the second trial, third trial, and so on. Okay, uh, t will be 1, right? So if, for example, x1 equals 1, x2 equals 1, x3 equals 0, x4 equals 1, let us say that somebody has performed like an infinite number of these trials. Okay, it really wouldn't matter what any of these are. Okay, the moment we see x1 equals 1, we'll say, yeah, t equals 1, because we succeed at the very first time.
Mhm.
Right, so do you see, we are not saying we are not performing the, so that is the distinction we are trying to make. Okay, we are not saying we are not performing the others. Okay, in some cases it may be useful to think as if like you're doing the rest. It's just that these do not matter. Right, so when we are writing x1 equals 1, we are writing x1 in combination with all other random variables. The event here, just like when you had two trials, right? So if you say, if you have two trials, right, when you say x1 equals 1, your event actually includes these two outcomes. Okay, the same way x1 equals 1, your event actually includes every other realization for x2, x3, and so on. Okay, does that make sense? Right, except that
Yeah.
right, but the moment you saw x1 equals 1, you know t equals 1, so you don't need to worry about what happened to the other random variables. It doesn't mean they don't exist. Okay, so but for t equals 2, if you just look at the random variable x2, that is not enough. Okay, because for, if t has to be 2, you needed to have failed in the first attempt. If you had succeeded in the first attempt, your t would have been 1. Okay, because t is the number of trials till success. Okay, so if x1 was 1, right, so if x1 was 1, your t is already 1, you succeeded in your first trial. Okay, you there is no question of t being equal to 2. T is the number of trials till success, till the first success. Okay, so maybe this will be more clear. So let's write it in a little more. I think I'm missing one. Yeah. Let's write it a little more. Maybe if I write it like this, it will be more clear. Okay. So T is the number of trials till the first success. Okay, so that has to exclude this part. Okay, so this is not, so t equals 2 is not the event x2 is 1. Okay, it is the event that x1 is 0 and x2 is 1. Okay, does that make sense? Right, so if the first time you succeeded was on your second trial, that means you must have failed on your first trial. If you had succeeded on your first trial, second time is not the first time. Okay, x2 is not the first time you succeeded. Okay, so what is the event t equals 3? Right, so x1 has to be 0, x2 has to be 0, and x3 is 1. Okay, and so on. Right, now t can take any value. Okay, t can take any integer, any positive number as its value. So the universe here, okay, is like Brandon was saying, the universe here is something like this, where we interpret this sequence we interpret it as x1 is 0, x2 is 1. Okay, this sequence we interpret as x1 equals 0, x2 equals 1, and x1, x2 are 0, and x3 is 1. Okay, okay, so we'll stop here. So we'll continue on Wednesday, so but you can continue asking questions.